We're going to close out all of the rest of the chi-square tests. We're going to do chi-square test of homogeneity and chi-square test of independence today. Excuse me. Both of them operate from a very similar standpoint when it comes to calculator and, you know, sort of the nuts and bolts, but they both are slightly different, and they're both way different from goodness of fit. We're going to move into these two tests, and we're going to be looking at, rather than a single categorical variable like color for M&Ms or color for Skittles or whatever, we're going to be looking at an interaction of more than one categorical variable. In the first one, we're going to be looking at two populations and one characteristic. So that would be a chi-square test of homogeneity. And we're going to be using regular chi-square, you know, observed minus expected square over expected, to answer the central issue to see whether or not a category proportion or the category proportions are the same for all of the populations. So we do need to compare observed counts to those that are expected. So since we're going to be doing this in 2 dimensions, we're not going to be doing kind of a flat, which is probably not the right word, but you know, a one-dimensional chi-square goodness of fit table. We're going to be doing a two-way table. So we're going to have marginal distributions and grand totals. You'll see it when we get to it. So we're looking at this as a formula that we're going to need. So calculating expected cell count will be row marginal total times column marginal total over grand total. I can't flip back and forth with this setup, so I will show this to you when we get to the next page. But these quantities would represent what would be expected if there are no differences between groups under studies. So that would be our null hypothesis, that the true population proportions are the same, whatever the context happens to be. HA is that those proportions would not be the same. So assumptions. Again, here is that formula for calculating expected counts. Now, we are going to probably rely on the calculator to do most of this work for us. But these formulas, this one and the one for degrees of freedom, these are things you ought to know in case they ask you like a multiple choice question on just a single cell, or having to do with calculating degrees of freedom by hand or whatever. All right, so we're going to use that to figure out if our expected values are at least 5. This first one, independent, we have not been using independent so far to have as one of our conditions. We've just been using random samples. What I researched on this is that a way to show that you have independence is if you have random samples. So if you look at this, it's a little bit redundant. It's saying the same thing twice. But if you feel the urgent need to write the word independent, I am not taking off for it. You know, this business of independence gets a little bit too picky for my liking, but you know, it is what it is. We need to add a third one because this is new, and it's that 10% rule. So population, or in this case it's plural, populations are at least 10 times the sample size. LEAST, 10 times the sample size. Actually, it would be, I guess, sample sizes. Plural. Now, when we do the test of independence, we won't be using plural. All right, so the name of this, chi-square test of homogeneity, we report the chi-square value, that's this, the p-value, the degrees of freedom, which we've been doing, and the chi-square value comes from observed minus expected squared divided by expected. You remember that. Every cell gets one of these. They all add up to your chi-square number. And the p-value would be as if we did chi-square CDF from your chi-square number to infinity with whatever your degrees of freedom are. Normally we just get the p-value for the calculator. So that would be your p-value, but it is a formula you can use. And this is new also, degrees of freedom. Since we're using a two-way table, it's the number of rows minus 1 times the number of columns minus 1. You remember for goodness of fit, it was just n minus 1, where n is the number of categories. But here we may have 5 rows and 3 columns. So for example, we would subtract 1 from the 5 to get 4, subtract 1 from the 3 to get 2. So that would be 8 degrees of freedom, for example. Okay? So you got to remember this. The conclusion, we're going to compare to an alpha, whatever our p-value is, or just use it based on how big or small the p-value is. We will either have sufficient or insufficient evidence to show the true category proportions are or aren't the same for all populations. If we reject, we do need a follow-up statement. So that is to show where the trends are, or what exactly we're seeing. Let's just move on to an example and you will see what I'm talking about. So this is, in the past, a number of professions were prohibited from advertising. This is true. When I was a kid, lawyers and doctors could not advertise. And then in 1977, the Supreme Court came along and said, nonsense to that. That's a violation of free speech. All right, I'm going to change to the next page. So bear with me while I pause. I can find out where my program is. I think there it is. So hang on while I pause. All right, so here's page 2. The article was or the study, should dentists advertise, compared the attitudes of consumers and dentists toward the advertising of dental services. All right, here we go. Separate random samples, right? And homogeneity requires 2 populations, so this 101 consumers comes from population number 1, and here's your 124 dentists, and that comes from population number 2. All right, so 2 separate populations, independent. They're asked to respond to the following. I favor the use of advertising by dentists to attract new patients. And you could answer strongly agree, agree, neutral, disagree, or strongly disagree. And here is the data presented in the article. Okay, a couple of things for this. First of all, the data points are here, 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 and here, and here. All of these numbers below are subtotals for how to answer this particular survey. And all the numbers here and here are all the subtotals for the dentists or consumers, the type of person we're dealing with. And this is the grand total, okay? So if I want to say get the, the expected count for this cell right here, I would do my row total, that's 101, so 101, times my column total, that would be 67, so 101 times 67, divided by my table total, which is here, 225, and that will give me the expected count, which is 30.08, and that is the same as what's down here. All right, so all of that is important, and you're thinking, wow, that's great. Do I have to do this 9 more times? And the answer to that would be no. You actually don't. So let me clean some of this out. We're going to let the calculator handle most of that. Okay, so here is your table, and let's see what we've got. Oh, another thing. See this number 4? I posed that question, is that a violation of assumptions? Remember, 5 or more? And a lot of kids said, yeah, it was, but it's not, because the at least 5 rule is for expected counts. These are all observed values, all right? They can be anything. They can be 1 or 2 or 20 or 80, but it's the expected that can't be below 5. So please don't make that mistake when you see it, because you probably will, all right? So, does there appear to be a difference between consumers and dentists with respects to attitude toward the advertising of dental services, tested at alpha of 0.05 level. Okay, so HO is the true population proportion for responses are the same for consumers and dentists, and HA is that they're not, all right? So this is part of what we have to report as, you know, our complete report. Where do they get these values, you know, the expected? It's not that they do that little formula for every single cell. Okay, so let's finish this up. Your assumptions, we're missing the 1, so for number 3, populations are at least 10 times the sample sizes. Sorry, you have to sit here while I write. All right, so what we're going to do is, in order to get the chi-square, the degrees of freedom, and the p-value, and all of these expected, we're going straight to the calculator, okay? And I'm going to do my work in a calculator page. I think you can get by if you do it in a scratch pad, but here's what we're going to do. The first thing we need to do is set up a matrix. So we need matrix and vector, create a matrix. And let's look back at this. That's not what I wanted. Where did it go? That's my mail. You don't want to see my mail. Where did it go? Okay, it's here. Okay. So let's see. We had rows go horizontally, and columns are like columns in a building. They're straight up and down. So 2, this is going to be a 2 rows by 1, 2, 3, 4, 5. 2 by 5. So that's the kind of matrix that we're going to create. And so let's go ahead and tell it. It's already got the 2 here for the rows. So tab down and change that to a 5, and then tab to OK. And we're going to enter all of the observed in those fields. Now the thing to remember is that you want to change the fields by hitting the tab key. So it'll be 34 tab and 49. Keep hitting tab. 9, 4, and 5. So 9 tab, 4 tab, 5. And then you can just use your click pad to go down and back over. And then it'll be 9 and 18, so 9 tab 18. And what's those last 3? 23, 28, and 46. So 23, 28, and 46. All right, those are all in. What you want to do now is to right arrow out. See, you want this outside of your matrix. And we need to store that as a letter. So Control var is store. And I'm going to pick A. Why not? Hit enter. Okay, now it's stored. To get everything we need, we're going to stay in here, go to menu, and run the test. So menu statistics, stat tests, and it's a 2-way chi-square test, not GOF, because they're going to ask you for like a list or something. Here they're going to ask you for a matrix. So click on that. Observe matrix is A. And tab to OK and hit enter. Okay, so if you look at the bottom of the page, this is the same chi-square number. This is the same p-value, although 0 would be fine. Remember, 4 degrees of freedom, 1 less from 2 is 1, 1 less from 5 is 4, 1 times 4 is 4. So we're going to write those down, or they're already there, but we would write them down. Now we need the come on brain, the expecteds. And so it's in a matrix. It's stored in a matrix. Also, those little bitty pieces of your chi-square number, like the things that make up all of those all this chi-square number, like we had in the bottom row of a goodness of fit table, those are listed too under comp matrix, but we kind of really don't need them, but you can use them if you want to. So go to var to expose this expected matrix, hit your variable key, and it's right here, stat exp matrix. So hit enter. See how it comes out bolded? It means something's stored there. So hit enter. And so that's where all the numbers come from. Now, if you need to scroll through here, you can just arrow up to select it and hit enter, and now you're in here. And there's a terrible amount of decimal places, but you can at least move around in here and copy them all down. And so that's where all of these numbers came from. Just 1 or 2 or 3 decimal places are fine. And that's where you get your chi-square, your degrees of freedom, right? And your p-value. So p is less than alpha, we're going to reject, and we have sufficient evidence to believe that there is a difference between consumers and dentists when it comes to attitudes toward advertising dental services. All right, so now you need to figure out what that difference is. So look closely and start looking at your observed and expected, especially for like right here. Do you see how more consumers strongly agree than what's expected? And then look over here at dentists. Here, they're more strongly disagreeing than expected. So there it is, right? Consumers tend to favor it. Dentists tend to not favor it. All right? So there's your chi-square test of homogeneity. Hopefully it's pretty doable. Now I need to pause because we're going to do a test of independence next. All right, I'm back. So here's a chi-square test of independence. And remember the homogeneity was 2 large samples taken from 2 population. This is 1 large sample taken from 1 population. And you're like here, we're picking just people and finding out what college experience they had. So it's just 1 population. We split it up into little groups. And we're looking at 2 characteristics, whether they like this cereal or whether they're kind of or don't like it, okay? So it's a little hard to tell homogeneity from independence. I find it kind of difficult. I mess it up more frequently than I'd care to admit. But there is something you can look for when it comes to independence. So let's see if we can pick it out. Tasty O's, a new cereal, was introduced into a local market last year to appeal to all adults. Because of its high nutritional content, management felt that the more informed, perhaps more affluent community would gravitate to the product. Therefore, advertising and promotion was slanted toward that group. Okay, they had a disappointing year. They weren't expecting it. There's been some speculation based on a focus group and panel research that taste preference for Tastios may be dependent on education. All right, that's a chi-square test of independence. Boom, right there. All right, so you're going to be looking for these things. Key words, for example, let's say related. So if you see that word, is one thing related to another? That's asking about independence. Associated. That's another key word. That means if they're related or dependent on each other. Depends on. How can you miss that one? Or just the word independent, which I believe is at the end of this problem. Yeah, right here. So there's probably other words too, but this is kind of your key. Also, it says they may be dependent on education. The more highly educated the consumer might be, the more he or she might prefer Tastios. So to test this hypothesis, we need to change this. It's actually 635, so 635 individuals were randomly sampled. That's 1 sample, right? 1 large sample. Were randomly sampled who had tried Tastios with the following results. Okay. You have 2 rows and 3 columns. So this is 2 by 3, which would mean this is going to be, that's going to be 2 degrees of freedom. Let me get rid of that. 1 more. So your degrees of freedom are going to equal 2. All right, 1 less than that times 1 less than that. And let me give you the subtotals here. So this adds down to 100. This adds down to 150. This adds down to 385. This adds across to 300. And oops, sorry, let me fix that. It's 300, it's thinking ahead, and this is 335. So you get a grand total, if you add across or add down, of 635, in case you need those numbers. We still need the, we've got the observed, we need the expected. All right, so assuming a valid random sample, test at a 0.05 level of significance whether the two variables in the population are independent. All right, so let's write this out. Okay, HO is the preference for Tastios and education level are independent. Okay, and HA is that they're not independent. All right, so let's go ahead and, so preference for Tastios depend on education level. Oops, you can tell it's been a long day. Get rid of, oh, get out of here. Depends on education level. All right, you're probably looking at that and saying, oh, that's all good, shouldn't be a problem. Except what could possibly go wrong? Could it be that you would switch these and put the dependent for HO and independent for HA? That happens all the time. So don't let it be you. Just remember, HO, no effect, no difference, does not equals whatever you tell me. Here it's independent, meaning no relationship. All right, so it matches up to what HO typically is. So independent is HO. Just remember that. All right, we're going to work this until we're going to have to go to the calculator. So sample, it's singular, is reasonably random, or was chosen randomly. That's given. If you look back at the problem. And the population is, and this is singular because we only drew one sample, population is at least 10 times the sample size. Okay, and the third one about your expected counts, we don't know that one. So it's about here where we need to default to the calculator. So here we go. And just hit enter and you can get down to an open field. And we're going to create a matrix again. So menu, matrix and vector, create a matrix. And remember it's 2 by 3. So leave the 2, change that to a 3, hit OK. And let's go ahead and put in these numbers just like we did before. And don't forget to tab. So 75, 90, and 135. And I'm going to go down and over, and then 25, 60, and 250. All right, remember, click outside, control stats, or var rather, control var. And I'm just going to say A again, it'll overwrite the previous one, hit enter. And then we just need to run the test. So menu, statistics, stat tests, chi-square two-way test. Again, the observed matrix is A. And hit OK. All right, so let's start recording some things and we'll come back and we'll get to the expected matrix. So let's see. Chi-square, that's what we're recording. We'll get to the others in a minute. So chi-square was 63.6148. That's pretty high. And the p-value was something times 10 to the negative, I don't know, but it was about 0. The degrees of freedom were 2. And the alpha that we're dealing with is 0.05. Clearly we're going to reject. But we've got to make sure that we've met assumptions. So let's go back to the calculator and go to vars, and we need your EXP matrix, and hit enter. All right, so let's go ahead and put those all in, and I'm just going to go ahead and do it from the key that I'm carrying around with me. So let's see, we've got to come up here. Now put these in parentheses, so 47.24. And under 90 it was 70.87. And your 135 was 181.89. Your 25 was 52.76. This was 79.13. And the 250 was 203.11. All right, so there we go. That's all of them, and they're all above 5. So all expected counts exceed 5. So let me get this up here. All right, so we're good to go. When we go to write the conclusion, p is less than alpha. All right, so since p is less than alpha, the results are significant, and we reject HO. You know, this is the usual stuff. And we reject HO. All right, if we're rejecting HO that they're independent, we're going to be claiming that they are dependent. All right, so since it's so close to 0, there is strong evidence to believe. You might be able to say this a little easier, a little shorter than me, that preference for Tastios depends on education level. There it is. Now, since we are saying that they're related, we're going to have to follow up and say how they're related. The trick here is to come up and to kind of highlight some major discrepancies that you see. Now, you can go back into the calculator. Let me at least show you. My mouse does not seem to want to work. Not sure what is going on with it. No problem. Oh, I think I know what I did wrong. Okay. If we go back to the calculator and we just want to see all of those component parts of your chi-square number, just go ahead and choose it, hit enter, and it looks like this is the lowest contributor, and it looks like this is the highest contributor. If that'll help you, great. If not, don't worry about it. Just come back here. And let's just look at, say, the college graduates, like right here, up in this. We were expecting 181, almost 182 of the college graduates to like Tastios. It's actually way less. So if we kind of divide this up between college and non-college, check this out right here. In fact, both of these. Neither one of these graduated from college. We were expecting about 47, we got 75. We were expecting about 71, we got 90. So what we're seeing here is that college people don't tend to prefer Tastios, but people that never graduated sort of do. All right? So let's just follow up by saying college graduates dislike Tastios more than those who don't graduate. Does that make sense? There it is. Chi-square test of independence, chi-square test of homogeneity.